Thank you for the chance to present this here. And I also realized that I had quite an ambitious title, and I do not like to change the title in the last minute, so I just changed the font sizes. Anyways, so I want to talk about constraint simulations. Is this an autoplay or something? What? Spacebar? Yeah. Spacebar is autoplay? Yeah. So, I want to talk about simulations and cosmic variance. And so, as doing cosmological simulations, usually I like to start with this picture. You all know that. It's a SMB microwave background. And then I say, well, we know the initial conditions very well, so we know gravity very well, so it's a very, very well-defined problem. But my point I want to make here is that actually we're starting from here. In other words, we use the power spectrum of the density fluctuations rather than the fluctuations themselves. And the difference here is that we do not use the phase information. And the consequence of this is that if you do a cosmological simulation, the structures that you simulate are not necessarily those that you observe in a given volume. In other words, the overdensity will be in different places, so this is what we call cosmic variance. And what you can do is you just run very big simulation boxes. So this is the Multidark project. So you go to gigaparsec boxes, and we did. In this 2.5 gigaparsec, we vary cosmology. And so the volume is big enough, so you can see the density here. So you can see a density field here, so it's way above the homogeneity scale of the universe. You can try to mitigate over any influence that an environment will have on the objects you actually want to study. So this doesn't work if you want to study very faint or less massive objects. As Anatoly said, in those box sizes, what you typically get is 10 to the 10 solar masses in mass resolution. So you need a different approach, and the approach you want to answer the question: can we disentangle structure formation, and can we do so for the one universe that we actually can observe? So the strategy here will be to constrain the initial phases of the density perturbation that you start from, to reproduce structures at final redshift. So, talking about observations, the best observations naturally are available in the local universe. And ideally, when you want to study the local universe, you ideally want to have a full sky volume limited survey, which of course is not available for us simulators. So what we started from was a 2-mass redshift survey. This is very complete in the sky. It's just a small zone of avoidance which, from the galactic disks, which obscures a few. Otherwise, it's very complete in the infrared. So from those galaxy catalog, we have our galaxy positions in redshift space. So this is a redshift survey, so we have them in redshift space. And so this is our starting point. And now, when we want to go to the initial phases, this is complicated, especially on small scales, because mode coupling actually hides the information that how the initial phases actually look like. So what we do is we use an iterative scheme. This is realized in the keygen code, which was developed by Francisco Quitara, my main collaborator in this project here. And this is a machine learning algorithm that iteratively solves structure formation. And it goes like this. You make an initial guess of the initial density perturbations and a corresponding field of meta traces. You evolve them forward in time with an efficient structure formation algorithm, and you compare your result with the desired density field. So let me add here that the desired density field is the galaxy's position, which we weight with the inverse of the selection function to get overdensity field. So you compare your meta tracer field with that one, and you only keep those meta traces that you can actually associate to galaxies. The other ones you throw away. And since you know the positions of the meta tracer at initial conditions, you can use those that you kept to, by Hamiltonian sampling, sample a new density field and a new overdensity field, then you can go forward again. So what you need for this is actually an efficient way to solve structure formation. And so we developed what we call augmented Lagrangian perturbation theory. This is really a second-order Lagrangian perturbation theory on large scales. And on small scales, we use a spherical collapse model because this is less prone to shell crossing, so it gives us higher accuracy on small scales. And so we can solve structure formation in this scheme here. And we also need to bring, of course, our resulting density field into redshift space. Now, since we do this in a forward way, we thought, yeah, well, we can as well solve the redshift space distortions in a forward way. So we actually use, for the coherent motions, we use the velocity field of the 2LPT. And for the small scale motions, we did some tests. First, we tried to compress the fingers of God in the data itself. This didn't work out quite so well. So I do not want to go into very detail here. Just let me mention that if you do the finger of God compression, especially in a local universe, you have as many problems as you see colors in this plot here. So what we do instead is we also model the fingers of God in a forward way. So we know the overdensities. So we assume a relation between the velocity dispersion and the overdensity, and then we can model the fingers of God also in the forward way. So this is what we decided to go for, which has less problems than the finger of God compression scheme. So now, having talked for several minutes about our scheme, what we actually end up with is this, which we call white noise, which is everything else but white noise because it has all the phase information of the local universe. But but it has all the properties of white noise in that it has a flat power spectrum, it has a variance of 1. And the big advantage of white noises is that you can easily add small-scale random modes. And we need to do so in order to boost our numerical resolution for the simulations. So you can use the white noise, you multiply it with the square root of the power spectrum, and then you can run your n-body simulation. So this is what we do. And I want to show you some results of of the full nonlinear density field of the n-body simulations that we can also bring into redshift space, and I want to show you the comparison with the galaxy distribution. So before we start with the n-body simulations, we want to cherry pick the best solutions from our iterative scheme. So since the scheme already runs thousands of iteration steps, we thought we can as well run it 1,200 times longer and pick the 25 best correlated with the galaxy field. So this is a cross power spectrum of the ALPT density fields, and we just picked the 25 best to simulate with n-body. This is the galaxy overdensity field. so the galaxies weighted with the inverse of the selection function, and we correlated with the solution of the perturbation theory density field. So we take those phases. We simulated with a moderate mass resolution of around 10 to the 8 times 10 to the 9. But we simulated a full ensemble of 25 simulations. We decided to go for a box size of 180 megaparsec per age base length, just because of the reason that the observations get very sparse at those distances, and the selection function drops very steeply. So constraint simulations have two basic properties. One is that it is a good n-body simulation. It's comparable to random simulations in terms of, in key properties such as this, the power spectrum. So this, the dotted lines, the colored dotted lines are the 25 simulated power spectra, and in gray you have 1 in 2 sigma of 25 random realizations, same box size, same cosmology. The same we did for the mass function. Again, in gray, 1 in 2 sigma of the random simulations, and in colors, the 25 constraint simulations. And you can see that they lie within errors of the random simulations. There's still a fluke here at around 2 times 10 to the 13, which might be due to cosmic variance or the particular structures in the local universe, which all of the constraint simulations resemble. And the other key property is, of course, how good is the resemblance to the local universe in the end. So what I'm showing here is, in grayscale, is the overdensity of the dark matter of the simulations brought to redshift space. And in red is the positions of the galaxies, just as they are. So what I'm showing here, this is supergalactic plane, x, y in megaparsec per age, and this is c, y. And you can see that we match the structures quite well. Now, this was qualitative. Quantitatively, we can again do a cross power spectrum. So this is galaxy density field cross-correlated with the n-body overdensity field brought to redshift space of the 25 simulations. And since we have an ensemble of simulations, we can look at what scales does the correlation, cross-correlation function go through 0. And since this is an ensemble, we can do an ensemble average. And this is how we measure the precision of our scheme, and we measure 2.6 roughly megaparsec per age. Now, again, visually, this is average over 25 over density fields. If you do it for the randoms, you would just see everything would be gray, one color. But maybe it's better to visualize it. Okay, this doesn't work in the PDF. Okay, anyways, so let me summarize what I wanted to present. So if you want to study low mass objects and want to deal with cosmic variance, want to study the influence of the environment, you need to resemble the structures as they are in observations. So we do constraint simulations, and the precision of these constraint simulations are around 2.6 megaparsec per age. With those simulations, we can study homogeneity and isotropy of the local universe just with every reconstruction. And since this precision is really a qualitative step in constraint simulations, we can actually do environmental studies, especially of bigger objects, where 2.6 megaparsec is only a factor 2 of virial radius. For example, the Coma or the Virgo cluster, which lie in our volume. Thank you.